47 liters. That is the volume of oxygen Chris Froome's heart pumped to his muscles during a single hour of racing at the 2015 Tour de France, a cardiovascular output so extreme it sits outside the measurable range of standard clinical equipment. His peak cardiac output during that stage, 40 liters per minute. The average adult male at maximum exertion produces roughly 20 to 22 liters per minute. Froome's heart, in other words, was functioning at nearly double the cardiovascular capacity of a fit, healthy non-athlete, not because he was trying harder, not because he was more motivated, but because the organ itself had been structurally and molecularly rebuilt over approximately 15 years of systematic physiological stress. That number 40 liters per minute is not a metaphor. It is a measured, documented physiological reality. And understanding how a human heart gets there is one of the most remarkable stories in all of sports biology. Here is what most people believe when they hear a number like that. They believe elite cyclists have extraordinary cardiac output because they train more hours, more kilometers, more suffering on mountain roads at 5 a.m. The assumption, the one that gets repeated in every cycling documentary, every sports biography, every coaching manual, is fundamentally a story about volume. Put in enough hours, and your heart gets stronger. That explanation sounds reasonable. It is also dangerously incomplete. Because here is the problem with the volume theory. Thousands of cyclists worldwide train at equivalent or greater volumes to Tour de France professionals, and never, not once in their careers, approach anything close to a 40 liter per minute cardiac output. Amateur endurance cyclists who train 20 hours per week for a decade plateau at cardiac outputs between 25 and 28 liters per minute. They put in the hours. The heart does not respond proportionally. So if training volume alone does not explain the gap, what does? The answer sits not in how many hours these athletes ride, but in what happens at the molecular level inside the heart muscle itself, a cascade of structural changes so specific, so targeted, and so biologically precise that researchers at the University of Lausanne spent nearly a decade trying to map it completely. What we are going to explore in this video is a specific biological phenomenon called exercise-induced cardiac remodeling, and more precisely, the molecular pathway through which sustained endurance training triggers a form of controlled, beneficial cardiac enlargement that is fundamentally different, at the cellular level, from the dangerous cardiac enlargement caused by disease. Researchers at Harvard Medical School, led by Dr. Anthony Rosenzweig, published landmark findings in 2012 in the gistal cell identifying the precise molecular switch, a signaling protein called IGF-1, or insulin-like growth factor 1, that separates the healthy, performance-enhancing cardiac growth of an elite endurance athlete from the deadly, pathological cardiac growth of heart failure. That distinction, healthy versus pathological cardiac growth, governed by a single molecular pathway, is the biological key that unlocks everything about elite cycling performance. SAV, and by the end of this video, you will understand not only what it is, but exactly how it works, what triggers it, how long it takes to build, and why it explains the performance gap between a Tour de France champion and a very fit amateur in a way that training volume simply cannot. To understand what happens to an elite cyclist's heart, you first need to understand what a heart actually is at the mechanical level, because most people's mental model of the heart is about 40 years out of date. The heart is not simply a pump. That framing, while useful for basic biology, misses what is actually happening at the tissue and cellular level. More precisely, the heart is a pressure-volume machine, a hollow muscular organ whose entire function can be described in terms of two variables: how much blood it can hold and how forcefully it can eject that blood. In clinical cardiology, these two variables are measured as end-diastolic volume, the amount of blood in the ventricle just before contraction, and ejection fraction, the percentage of that blood that actually gets pushed out with each beat. In a sedentary adult, the left ventricle holds approximately 120 milliliters of blood at peak filling. It ejects roughly 70 milliliters per beat, an ejection fraction of about 58%. At a resting heart rate of 70 beats per minute, that produces a cardiac output of about 4.9 liters per minute, enough to sustain basic metabolic function. Not enough to power a human being up an alpine mountain pass at 25 kilometers per hour for 4 consecutive hours. But this is where it gets strange. When you ask most people, including many fitness professionals, how the heart increases its output during intense exercise, the answer they give is, the heart beats faster. And that is true. Heart rate rises dramatically during exercise. But here is what the data actually shows. In elite endurance athletes, heart rate increase accounts for only part of the cardiac output story. The other part, the part that separates elite from amateur, is something called the Frank-Starling mechanism, operating at a scale that simply is not accessible to an untrained heart. The Frank-Starling mechanism, named after physiologists Otto Frank and Ernest Starling, who described it in the late 19th and early 20th centuries, states that the force of cardiac contraction is directly proportional to the degree to which the cardiac muscle is stretched before contraction. In simpler, mechanical terms, the more you fill the ventricle, the more forcefully it will empty. Think of it like a rubber band. A rubber band that is barely stretched produces minimal elastic recoil when released. A rubber band stretched to near its maximum elastic capacity snaps back with considerably more force. The cardiac ventricle operates on the same principle within physiological limits. The more blood that flows in during diastole, the more powerfully it gets ejected during systole. Now here is where elite cycling adaptation enters the picture. In a trained endurance athlete, the left ventricle has physically enlarged, not through disease, not through damage, but through a specific regulated process of cellular expansion that increases the chamber's capacity, its end diastolic volume, dramatically. Research published in the Journal of the American College of Cardiology in 2014 by Dr. Stefano Castelli and colleagues measured the left ventricular end diastolic volumes of professional cyclists and found average values of 195 to 210 milliliters compared to the sedentary adult baseline of 120 milliliters. That is a 65 to 75% increase in the raw volume capacity of the heart's primary pumping chamber. More volume in. Frank Starling kicks in. More force generated per beat. More blood ejected per contraction. At a heart rate of 180 beats per minute, which a Tour de France climber sustains for hours, that enlarged ventricle is not ejecting 70 milliliters per beat. It is ejecting closer to 150 to 180 milliliters per beat. Multiply 170 milliliters by 180 beats per minute, and you approach a cardiac output of over 30 liters per minute before you have even accounted for the additional adaptations in the heart's structural efficiency that accumulate with years of training. Here's what nobody tells you. That calculation assumes the heart wall is also strong enough to generate sufficient pressure to eject that larger volume with enough force to perfuse muscles throughout the body at exercise intensity. And this is where the second half of the cardiac remodeling story begins, because ventricular enlargement alone, without a proportional increase in wall thickness and myocardial contractility, would actually reduce performance rather than enhance it. This is the critical distinction between what cardiologists call eccentric hypertrophy, the athlete's adaptation, and dilated cardiomyopathy, the disease state. Both involve ventricular enlargement, but in eccentric hypertrophy, wall thickness increases proportionally to chamber volume, preserving or even improving wall stress and contractile efficiency. In dilated cardiomyopathy, the wall thins as the chamber expands, reducing contractile force per unit of wall area. The molecular switch that determines which pathway the heart takes healthy growth or pathological dilation is what researchers spent decades trying to identify. And when they found it, the answer was both elegant and, in retrospect, obvious. To understand how the elite cyclist's heart operates under the actual conditions of a Tour de France mountain stage, we need to think carefully about what the cardiovascular system is being asked to do, and what the cascading biological consequences of that demand are at every level, from organ to tissue to cell to molecule. During a Category 1 climb at Tour de France intensity, a professional cyclist's working muscles, primarily the quadriceps, hamstrings, gluteus maximus, and hip flexors, are consuming oxygen at a rate of approximately 5 to 6 liters per minute. That is the athlete's VO2 volume of oxygen consumed per minute. For comparison, The average untrained adult has a VO2 max, the maximum oxygen consumption rate achievable at peak exercise, of approximately 35 to 40 milliliters of oxygen per kilogram of body weight per minute. A Tour de France climber like Chris Froome has a documented VO2 max in the range of 84 to 88 milliliters per kilogram per minute. That is more than double the average untrained adult's capacity, and it directly reflects the heart's ability to deliver oxygenated blood and the muscle's ability to extract and use that oxygen at a rate that most cardiovascular systems simply cannot sustain. But raw VO2 max, as remarkable as it is, tells only part of the performance story. What matters on a mountain stage is not peak oxygen consumption capacity, it is sustainable oxygen consumption over multi-hour efforts. And this is where cardiac output efficiency becomes decisive. And this next part is what the data actually shows. The reason elite cyclists can sustain efforts at 85 to 90% of their VO2 max for extended periods, while an amateur cyclist who attempts the same relative intensity would be forced to stop within 20 to 30 minutes, comes down to a phenomenon called cardiac output reserve, and how efficiently it is deployed. Here is the mechanism in precise terms. At rest, the human body distributes cardiac output roughly as follows. Approximately 15 to 20% goes to skeletal muscle, 15 to 20% to the digestive system, 20 to 25% to the kidneys, and the remainder distributed among the brain, heart muscle itself, skin, and other organs. During maximal exercise, this distribution undergoes a radical redistribution. Blood flow to the digestive system drops to approximately 3 to 5% of cardiac output. Renal blood flow drops similarly. Skin blood flow increases modestly for thermoregulation, and skeletal muscle blood flow rises to capture 80 to 85% of total cardiac output. In an average person reaching maximal cardiac output of 20 liters per minute, skeletal muscle therefore receives roughly 16 to 17 liters of blood per minute. In an elite cyclist with a cardiac output of 40 liters per minute, skeletal muscle receives 32 to 34 liters of blood per minute, nearly twice the delivery of oxygen-carrying red blood cells to the tissue that actually needs it. But here is where the adaptation story deepens beyond the heart itself. If you simply doubled the blood flow to muscles without simultaneously increasing the capillary network within those muscles, the blood would move through too quickly. Oxygen exchange would be inefficient, and much of the additional cardiac output would be physiologically wasted. The body does not allow this inefficiency. Research by Dr. Ylva Helston at the University of Copenhagen, published in 2016, demonstrated that elite endurance athletes develop significantly denser capillary networks within their working muscles, a process called angiogenesis driven by a signaling molecule called VEGF, or vascular endothelial growth factor, that is upregulated during sustained aerobic exercise. In practical terms, the muscle of an elite cyclist contains approximately 5 to 7 capillaries per muscle fiber. An untrained adult has approximately 3 to 4. That difference, seemingly small in absolute terms, means that when 34 liters of blood per minute arrives at the muscle, it enters a distribution network dense enough to slow transit time sufficiently for efficient oxygen unloading from hemoglobin to myoglobin, and ultimately into the mitochondria where ATP production actually occurs. The heart enlarges to deliver more volume. The vascular system expands to distribute it efficiently. The muscle tissue rebuilds itself to extract it optimally. These adaptations do not operate independently, they are a coordinated biological system, each component's adaptation enabling and demanding the others. But this is where it gets strange. When cardiac physiologists at the University of Gothenburg began studying what triggers the heart's enlargement in the first place, searching for the upstream signal that initiates the entire cascade, they found something that surprised them. The trigger for cardiac chamber enlargement is not, as many had assumed, primarily a response to increased cardiac work. It is primarily a response to increased cardiac filling volume, the amount of blood returning to the heart per beat during exercise. This is a crucial mechanistic distinction. When you exercise at high intensity, your working muscles act as secondary pumps. Their rhythmic contractions squeeze blood through the venous system back toward the heart with considerably more force than at rest. This phenomenon, called the skeletal muscle pump, dramatically increases venous return, the volume of blood arriving at the right atrium per minute. In an untrained heart, this increased venous return causes modest Frank Starling-driven increases in stroke volume. But the chamber walls are relatively inelastic, and the volume increase is constrained. Over years of training, the cardiac chamber walls undergo a process of sarcomere addition. In series, the individual contractile units of cardiac muscle cells are literally lengthened by the addition of new protein subunits, making the chamber wall more compliant, more able to stretch without generating the wall stress that would trigger pathological remodeling. This is the cellular mechanism behind the enlarged, compliant, performance-optimized athlete's heart, and it is driven not primarily by the heart working harder, but by the heart being repeatedly asked to accommodate larger filling volumes, stretch more thoroughly, and recoil more forcefully thousands of times per training session, across thousands of training sessions over years. The numbers that result from this process are, in clinical terms, extraordinary. A study published in the European Heart Journal in 2018 measuring cardiac dimensions in professional cyclists found left ventricular end-diastolic diameters averaging 58 to 62 millimeters compared to a clinical normal range of 42 to 55 millimeters. Left ventricular mass, the total weight of the heart muscle itself, averaged 270 to 310 grams in the professional cyclists, compared to a population norm of 140 to 180 grams. The elite cyclist's heart, by mass, is nearly twice the size of an average adult's heart, and every gram of that additional mass represents functional, contractile muscle, not fat, not scar tissue, not pathological fibrosis, but organized, vascularized, electrically coordinated cardiac muscle that exists for one purpose: to move blood at extraordinary rates. The question that naturally follows is, how long does this take? And more specifically, is there a point in an athlete's development where the cardiac remodeling begins, and a point where it plateaus? Is any of it genetically determined, and can it be reversed? The timeline of cardiac adaptation in elite cyclists is more precisely documented than almost any other physiological adaptation in sports science, largely because of a longitudinal study conducted by Dr. Sanjay Sharma and colleagues at St. George's University of London, a research program that tracked cardiac dimensions in junior and professional cyclists across a span of more than a decade. Here is what they found. In cyclists who begin systematic endurance training between ages 14 and 16, measurable left ventricular enlargement defined as a left ventricular end-diastolic diameter exceeding the age-matched 95th population percentile begins to appear within approximately 18 to 24 months of sustained training at volumes above 12 hours per week. The initial adaptation in those first 2 years is primarily chamber dilation. The volume of the ventricle increases without a proportional increase in wall thickness. This is the point at which many sports cardiologists, seeing these athletes' scans for the first time, experience diagnostic anxiety because a dilated left ventricle in a non-athlete is one of the cardinal signs of dilated cardiomyopathy. But in the athlete, the dilation is followed, over the subsequent 3 to 5 years of continued training, by a proportional increase in wall thickness, the eccentric hypertrophy completing itself into a balanced, structurally sound, high-performance configuration. By years 5 through 8 of systematic training, the cardiac dimensions begin to approach their genetically bounded ceiling. Here's what nobody tells you. That phrase, genetically bounded ceiling, is where the answer to the genetics question lives, and it is more nuanced than the popular framing of some people are just born with it. Research published in the British Journal of Sports Medicine in 2017 identified that variation in the ACE gene, the angiotensin-converting enzyme gene, significantly modulates the degree of cardiac hypertrophy achieved in response to identical training stimuli. Athletes carrying 2 copies of the insertion allele of the ACE gene, the 2 genotype, show significantly greater left ventricular mass increases in response to endurance training than athletes with the deletion-deletion DD genotype, given identical training loads. What this means in practical terms is that 2 cyclists training side by side, at identical volumes, intensities, and for identical durations, will not develop identical hearts. The athlete with the 2ACE genotype will achieve greater cardiac chamber enlargement, greater wall mass development, and ultimately a higher ceiling for cardiac output, not because of anything they did differently in training, but because of the molecular sensitivity of their cardiac tissue to the growth signals generated by training. This is not determinism. Training is still required to activate these genetic advantages. An ACE2 genotype in a sedentary person produces no cardiac advantage whatsoever. The gene is a sensitivity amplifier, not a performance guarantee, but it explains a significant portion of the variance between athletes training at the same level. The research estimates that genetic factors account for approximately 40 to 50% of the variance. In VO2 max response to training, a finding that has been replicated across multiple population studies, most notably in the landmark Heritage Family Study conducted by Dr. Ciard and colleagues, which followed 481 sedentary adults across 5 months of standardized endurance training, and found that VO2 max improvements range from near zero to over 100%, with the variance clustering strongly within biological families. The adaptation story for cardiac remodeling, then, is best described as a gene-environment interaction. The environmental stimulus sustained. Progressive endurance training activates a genetic program for cardiac enlargement, whose ultimate magnitude is partly determined by the specific variant of regulatory genes the athlete was born with. Elite cyclists at the Tour de France level represent, overwhelmingly, the intersection of the highest genetic sensitivity to cardiac adaptation and the most systematic, sustained application of the training stimulus required to fully express that genetic potential. Chris Froome, Greg LeMond, Miguel Indurain's resting heart rate was documented at 28 beats per minute, reflecting a stroke volume so extraordinarily large that his heart needed to beat only 28 times per minute to maintain adequate resting cardiac output. These athletes are not exceptional because they trained more than everyone else. They are exceptional because their biology responded to training in ways that most humans' cardiovascular systems are not genetically equipped to replicate at the same magnitude. And this is where it stops being about elite cyclists and starts being about you. The biological principle operating throughout everything we have discussed can be stated as a specific physiological law, one that applies not only to elite cyclists, but to every human cardiovascular system at every level of fitness. It is called Wolff's Law of Cardiac Remodeling, an extension of Julius Wolff's 19th century observation that biological tissues remodel in response to the mechanical stresses placed upon them. For bone, the law describes how weight-bearing stress drives increased bone density. The heart, the principle is identical in structure. The heart remodels its architecture in direct response to the chronic mechanical demands placed upon it. The key variables that determine the direction and magnitude of cardiac remodeling are these. First, the type of stress applied. Pressure overload, as occurs in hypertension or in strength training, where the heart must pump against very high vascular resistance, drives concentric hypertrophy. The ventricle wall thickens without a proportional increase in chamber volume. Volume overload, as occurs in sustained aerobic exercise, where the heart must accommodate and pump large volumes of blood, continuously drives eccentric hypertrophy. Chamber volume increases with proportional wall thickening. This distinction explains why powerlifters and cyclists, despite both being among the most cardiovascularly trained athletes on Earth, develop structurally different hearts. The powerlifter's heart has thick walls optimized for brief, intense pressure generation. The cyclist's heart has large chambers optimized for sustained, high-volume output. Same organ, same principle, completely different architectural outcome determined entirely by the type of mechanical stress applied. Second, the duration and frequency of the stress. The cardiac remodeling response is not triggered by a single training session, no matter how intense. It requires the repeated chronic application of the mechanical stimulus. Research by Dr. Domenico Corrado at the University of Padova identified that meaningful cardiac chamber enlargement requires a minimum of approximately 4 to 5 hours of sustained aerobic training per week for a period of at least 6 to 12 months before measurable structural changes become detectable on echocardiogram. This chronic stimulus requirement is why the heart responds to endurance training in a fundamentally different time frame than, say, skeletal muscle, which begins showing measurable hypertrophy within 6 to 8 weeks of resistance training. Cardiac structural remodeling is a slow, deliberate process, precisely because the consequences of premature or structurally unsound cardiac growth would be literally fatal. Third, and most importantly, the law operates in reverse. Detraining produces cardiac remodeling in the opposite direction. Studies measuring cardiac dimensions in former elite endurance athletes, including research on retired Olympic rowers and cyclists, show that left ventricular end diastolic volume decreases measurably within 3 to 4 weeks of complete detraining and returns to near baseline within 3 to 6 months of cessation of systematic training. The heart is not a bank account. You cannot deposit decades of cardiac adaptation and then withdraw it indefinitely without making further deposits. The adaptation requires ongoing stimulus to be maintained, a fact that has significant implications not only for elite athletes managing their training loads, but for understanding what happens physiologically to every human heart as activity levels change across a lifetime. This same law operates in a cardiovascular patient who begins a medically supervised exercise program after years of sedentary living. Their heart will begin remodeling toward a more efficient architecture within weeks. Operates in a pregnant woman whose cardiac output increases by 30 to 50% during pregnancy to accommodate fetal circulation demands, driving temporary physiological cardiac enlargement that resolves postpartum. It operates in individuals living at high altitude whose hearts adapt to chronic mild hypoxia by increasing cardiac output efficiency. One biological law, infinite applications. The heart is always remodeling, always responding to what you ask of it, within the boundaries set by your genetics, and it never stops. So now, when you notice something that you have probably noticed before that moment during a sustained aerobic effort, maybe 20 or 30 minutes into a run or a ride, when your breathing suddenly finds a rhythm, when your heart rate stabilizes, when the effort that felt unsustainable a few minutes ago starts to feel manageable, you know what is actually happening. That is not a mental adjustment. That is not a psychological shift. That is your cardiovascular system completing its redistribution sequence, blood flow shifting from digestive organs to working muscle. Stroke volume rising as venous return increases. The Frank-Starling mechanism engaging more fully as filling volume climbs. Cardiac output stabilizing at a level that matches your metabolic demand. And when you hear that an elite cyclist's heart is twice the mass of an average person's, you no longer need to translate that into vague admiration. You now understand the specific molecular and structural journey that produces that mass, the sarcomere additions in series. The VEGF-driven angiogenesis, the Frank-Starling optimization, the ACE gene sensitivity that determines how much of the training stimulus gets converted into structural change. You understand that the 40-liter per minute cardiac output of a Tour de France climber is not magic, and it is not simply the result of harder work. It is the result of a very specific biological program, gene-environment interaction, executed over 15 to 20 years of progressive mechanical stress, producing a structurally and molecularly distinct organ from the one that athlete was born with. You also understand something more unsettling. Why the gap between elite and amateur is not primarily a gap in effort, but a gap in biological response to effort. The elite cyclist and the dedicated amateur are not separated by how hard they try. They are separated, in significant part, by the molecular sensitivity of their cardiovascular tissue to the adaptation signals generated by identical training loads. That is not a reason for cynicism. It is a reason for precision. Understanding the actual mechanism means you can make more informed decisions about your own cardiovascular training, knowing that the stimulus required is chronic, not acute, that the adaptation is directional, not generic, and that the heart you have at 50 is not the heart you were given at birth, but the one you have, quite literally, built cell by cell, sarcomere by sarcomere, over the accumulated mechanical stress of your life. The biology does not care about your competitive ranking. It responds to the stimulus. Every heart remodeling at whatever level runner, cyclist, swimmer, Someone walking briskly is building a different heart than they would have if they stayed on the couch. The Tour de France is the extreme expression of a universal biological principle. And now you can see exactly where the extreme ends and the principle begins. But here is the question that the cardiac adaptation story leaves unresolved, and it is the one that sports physiologists are currently most actively debating. We know that the elite cyclist's heart is structurally enlarged. We know it pumps more blood per beat. We know it produces more cardiac output per minute. But there is a ceiling to cardiac output, a point beyond which the heart physically cannot pump faster or fill more completely. And several athletes in the documented historical record appear to approach or reach that ceiling. So what separates the athletes who can sustain 90% of their VO2 max for 4 hours from those who can only sustain it for 2, even when their cardiac outputs are essentially identical? The answer is not in the heart at all. It is in the muscle. Specifically, it is in a cellular structure that most people know exists, but almost nobody understands at the mechanistic level, the mitochondrion. SAR. And the adaptation story of the mitochondria in elite endurance athletes makes the cardiac story look simple by comparison. That is the subject of the next video on this channel. The specific molecular mechanism by which endurance training triggers mitochondrial biogenesis, the creation of new mitochondria within muscle cells, and why the density and efficiency of those mitochondria determines whether an athlete can sustain extraordinary output indefinitely or hit a wall at the edge of their cardiac capacity. If the heart is the engine displacement, mitochondria are the fuel injection system. And the engineering story behind elite mitochondrial adaptation is, if anything, more precise and more counterintuitive than anything we covered today. Subscribe to the Performance Lab so you are notified the moment that video goes live. And if you want to understand the complete cardiovascular picture before we move to the cellular level, the video on VO2 max, why the number matters far less than how close to it you can operate, is linked on screen now. The biology is always more interesting than the biography. We'll see you in the lab.